SRAMs are organized as an array of memory locations, where a memory access is either reading or writing all the bits in a single location. Here we see the component layout for an 8-location SRAM array, where each location holds 6 bits of data. You can see that the individual bit cells are organized as 8 rows, 1 row per location, by 6 columns, 1 column per bit in each memory word. The circuitry around the periphery is used to decode addresses and support read and write operations. To access the SRAM, we needed to provide enough address bits to uniquely specify the location. In this case, we need 3 address lines to select one of the 8 memory locations. The address decoder logic sets one of the 8 word lines, the horizontal wires in the array, high to enable a particular row, location, for the upcoming access. The remaining word lines are set low, disabling the cells they control. The active word line enables each of the SRAM bit cells on the selected row, connecting each cell to a pair of bit lines, vertical wires in the array. During read operations, the bit lines carry the analog signals from the enabled bit cells to the sense amplifiers, which convert the analog signals to digital data. During write operations, incoming data is driven onto the bit lines to be stored into the enabled bit cells. Larger SRAMs will have a more complex organization in order to minimize the length, and hence the capacitance, of the bit lines. The heart of the SRAM are the bit cells. The typical cell has 2 CMOS inverters wired in a positive feedback loop to create a bistable storage element. The diagram on the right shows the 2 stable configurations. In the top configuration, the cell is storing a 1-bit. In the bottom configuration, it's storing a 0-bit. The cell provides stable storage in the sense that as long as there's power, the noise immunity of the inverters will ensure that the logic values will be maintained even if there's electrical noise on either inverter input. Both sides of the feedback loop are connected via access FETs to the 2 vertical bit lines. When the word line connected to the gates of the access FETs is high, the FETs are on. In other words, they will make an electrical connection between the cell's internal circuitry and the bit lines. When the word line is low, the access FETs are off, and the bistable feedback loop is isolated from the bit lines and will happily maintain the stored value as long as there's power. During a read operation, the drivers first recharge all the bit lines to VDD, in other words, a logical 1 value, and then disconnect, leaving the bit lines floating at 1. Then the address decoder sets one of the word lines high, connecting a row of bit cells to their bit lines. Each cell in the selected row then pulls one of its 2 bit lines to ground. In this example, it's the right bit line that's pulled low. Transitions on the bit lines are slow since the bit line has a large total capacitance and the MOSFETs in the 2 inverters are small to keep the cell as small as possible. The large capacitance comes partly from the bit line's length and partly from the diffusion capacitance of the access FETs in the other cells in the same column. Rather than wait for the bit line to reach a valid logic level, sense amplifiers are used to quickly detect the small voltage difference developing between the 2 bit lines and generate the appropriate digital output. Since detecting small changes in a voltage is very sensitive to electrical noise, the SRAM uses a pair of bit lines for each bit and a differential sense amplifier to provide greater noise immunity. As you can see, designing a low-latency SRAM involves a lot of expertise with the analog behavior of MOSFETs and some cleverness to ensure electrical noise will not interfere with the correct operation of the circuitry. Write operations start by driving the bit lines to the appropriate values. In the example shown here, we want to write a 0-bit into the cell, so the left bit line is set to ground and the right bit line is set to VDD. As before, the address decoder then sets one of the word lines high, selecting all the cells in a particular row for the write operation. The drivers have much larger MOSFETs than those in the cell's inverters, so the internal signals in the enabled cells are forced to the values on the bit lines, and the bistable circuits flip into the new stable configuration. We're basically shortening together the outputs of the driver and the internal inverter, so this is another analog operation. This would be a no-no in a strictly digital circuit. Since NFETs usually carry much higher source drain currents than PFETs of the same width, and given the threshold drop of the NFET access transistor, almost all the work of the write is performed by the large NFET pull-down transistor connected to the bit line with the zero value, which easily overpowers the small PFET pull-up of the inverters in the cell. Again, SRAM designers need a lot of expertise to correctly balance the sizes of MOSFETs to ensure fast and reliable write operations. It's not hard to augment the SRAM to support multiple read-write ports, a handy addition for register file circuits. We'll do this by adding additional sets of word lines, bit lines, and drivers and sense apps. This will give us multiple paths to independently access the bistable storage elements in the various rows of the memory array. With an N-port SRAM, for each bit we'll need N word lines, 2N bit lines, and 2N access FETs. The additional word lines increase the effective height of the cell, and the additional bit lines increase the effective width of the cell. And so the area required by all these wires quickly dominates the size of the SRAM. Since both the height and width of a cell increase when adding ports, the overall area grows as the square of the number of read-write ports. So one has to take care not to gratuitously add ports, lest the cost of the SRAM get out of hand. In summary, the circuitry for the SRAM is organized as an array of bit cells, with one row for each memory location and one column for each bit in a location. Each bit is stored by two inverters connected to form a bistable storage element. Reads and writes are essentially analog operations performed via the bit lines and access FETs. The SRAM uses 6 MOSFETs for each bit cell. Can we do better? What's the minimum number of MOSFETs needed to store a single bit of information?